So finding the equation of a plane passing through these three coordinates. Now, the first thing that you're going to look for when you're writing the equation of a plane is to see if there's a commonality between any of the coordinates, right? You see how the x values vary from 6 to 0 to 1. The z values vary from 9 to 4 to -3, but the y values always remain the same, right? And so in number 1, we wrote our equation as x equals 3 for all values of y and z. So really what we're getting at here is the same idea, except y is equal to -2 for all values of x and z. Now you can verify it pretty easily just by popping it into Geogebra, y equals -2, and you can see that you have a plane. That's all well and good. Yeah, you type in any of these forms, x equals, y equals, or z equals, you're going to get a plane. We want to know if this plane is correct. So we would pop in the coordinates, 6, -2. You probably don't have to pop them all in. If you get 1 or 2 that fall on the line or on the plane, then you're good to go. But if you want to cross the T's and dot the I's, and you go the distance and pop them all in. All right, so I got my points in and I got my plane going. Now, it's kind of hard to see, but I got B and C there. They're definitely, well, I was going to say they're definitely on the plane, but they look like they're on the, oh, I just moved C, dang it. Undo. So, let me go hit home. It'll reorient it. But if you do like a top-down view of it, it's a little easier to see. So you can see that E and C are right on the plane. I lost track of where A ended up. I'm sure it's, well, the Z value is 9, so it's off the screen on the high end. So 2 out of 3 ain't bad. If it turned out that 9 was somewhere completely far afield, then I would look to check my work, but it's not going to be the case in this situation, right? So obviously, you know, I'm working with a narrow field here. If I increase it, it's a little bit easier to maneuver. So there's my A. So bring it back in. I find that working with a computer or a tablet at minimum is probably the best when you're dealing with GeoGebra because of the, you know, issues like this, right? Doing it on a phone, I mean, you can get away with the simple computations, but when it comes to the, you know, the visual stuff, it becomes a little trickier, right? Distance formula. So we have a distance formula in 3 dimensions, and it's pretty straightforward because all we're really doing is applying the same distance formula we always knew and loved, except now we're applying it in a 3rd dimension, right? So I'm just going to take you through the origin story of this real quick. Not too quick, but quick, you know. So I want that to be red and I want it to be red. So this is, oof. This is what a right triangle would look like in 2 dimensions. All right, but it's part of a 3-dimensional rendering, which is why it doesn't look like a right triangle. Right, it's a perspective drawing of that right triangle, but it gets the job done. What you're doing is you're kind of imagining that you're taking a top-down view from the z-axis, looking down upon the xy plane. And if you were to do that, that's what you would see. You would see a nice right triangle, and then that right triangle is going to have sides. Right, those sides would be A, B, and C. All right. Now, we also have, if we're trying to find the distance between 2 points in space, so for example, in this case, 0, 5, 0 and -3, 0, 2, we need to account for elevation, the height off of the off of the XY plane, right? So that's where this vertical segment comes into play, right? So we get another right angle here, another perspective drawing of a right triangle, right? Poor quality, of course, but it's still there, right? The sides of this one are going to be, well, we got one leg is the C that was the hypotenuse of the right triangle in the XY plane. We'll use D for distance to represent the hypotenuse in the three-dimensional coordinate system, right? And also, you know, A, B, C, D. And so that brings us to E for that vertical side. So I would want to have C squared plus E squared be equal to D squared, right? But I also know that A squared plus B squared is equal to C squared. So by substitution, I can replace the C squared with an A squared plus B squared. So we get A squared plus B squared plus, well, E squared, kind of weird, but is equal to D squared. All right. Now we can take square roots and stuff like that, and that would work. But we also, I mean, A versus B versus E, we don't like the sound of that because we're working with coordinates, right? Now, if I tell you that the A value is the difference between corresponding X coordinates, making the B the difference between Y coordinates, and the E would be the difference between Z coordinates, then you start getting the picture here, right? So difference between the X coordinates, the Y coordinates, and the Z coordinates. So actually, you know what I'll do? I might actually have a fighting chance of making this look pretty nice. I'll just label that right there. Difference between coordinates, specifically the X's, the Y's, and the Z's. Right? And that's because if you look at the A value, it's a displacement along the x-axis. Yeah, it's the negative x-axis, but it's still the x-axis. The B values are a displacement along the y-axis. And even though E isn't specifically on the z-axis, it still represents a displacement along the z-axis. Right? So that's the abridged version of the derivation of the formula. Applying the formula is much, much easier because it's D equals the square root, because it would be the result of just taking the square root of that equation that we just came up with. Zero minus -3, -3 minus 0 doesn't make a difference. I'll do -3 minus 0. Plus 0 minus 5, just be consistent. Plus 2 minus 0. All right, and then we crunch those numbers, and then we pretty much have it. I mean, you may have to pop it into a calculator if the numbers aren't too neighborly, but we're looking at, we got a 9 here, we got a 25, and we got a 4, all under the radical. Oops. So we're talking, what, 38? Root 38. Product of primes 2 and 19, so that's not simplifying. So radical 38 units, linear units. So whatever the units are in the context of the situation would be the appropriate units. Right. So that's all there is to distance. It's not very complicated, right? Especially since it's reliant on prior knowledge. You know, so if you knew the distance formula, you know, I'll just mark it up here. If you knew the distance formula, which is everything but what I just scribbled out, then adding this little extra component is not very complicated. It also expands or extends into the fourth dimension and the nth dimension. It keeps going. So you just keep adding components to it, right? So it's just coming up with a visual for the fourth dimension is challenging, to say the least. We save that for the end of the course. Right? We need some more foundational stuff before we can hope to understand that. Right? But at least the visual stuff. We'll work with the fourth dimension prior to the end of the course, just not the visual components. All right. So then we have a variation on the distance formula, which is the equation of a sphere. Right? The standard form equation of a sphere, pretty straightforward, but it does rely on you being able to determine what the radius is. Right? So the radius of the circle, or I'm sorry, the sphere, is going to be based off of the distance. So, you know, in number one, where it says find the standard equation of a sphere with center and point, it's implied that the very first thing that you would do would be to come up with the distance related to those points, between those points. Right? So R for radius is going to end up being D for distance. You know, we just got to make that adjustment. So D would be equal to 10 minus -1, so 10 plus 1 squared, plus 7 minus 3 squared, plus 4 minus -2, so 4 plus 2 squared, all under the radical. All right, so 10 plus 1, 11 squared, 121. 4 squared, 16. 6 squared, 36. All under a radical. So 137, 167, 173, I think. Maybe. Yeah, I think so. All right, so that's the radius. So if we're popping it into this model, then what we're doing is we're identifying the center. That center has values A, B, C. And so our equation is going to be x minus the A value squared plus y minus the B value squared. Let me go off the end here. Plus z minus the C value, so 4 squared. And then that's going to be equal to that radical 173 squared, which is just going to become a plain old 173. All right, so just cleaning it up a little bit. And I'll just box it up so that we know. All right, so then, you know, I always have the mentality that, like, I'm not going to do all this work and then not check it. So, yeah, I said, I didn't save, I said clear all. Yeah, okay. Yeah, I always want to check it because anytime I do work, I want to make sure I did that work correctly, you know, except when I'm teaching. Because that's what you're all here for. I believe that's the only reason too, just to make sure that I don't make mistakes. There's nothing to do with getting credits and graduating and stuff like that. -4 squared equals 173. That's a pretty alarming looking figure. It doesn't look like anything at all like a sphere, but what we do, again, because it can be a little tricky when you get into the smaller screens, it looks very much like a sphere if you zoom out, right? So that is definitely a sphere, so we're good there. And then, the center is going to be tough to see, but you can plot the other point, -132. That should be a point on the sphere. -2. Oops, looking at the wrong thing. All right, so I got that point that's kind of living there right on the edge. You can see it. Geogebra does a pretty good job of giving points which, they don't have any size, just locations, giving them some depth so that you can actually visualize what they look like. So here's my point A, and that's pretty clearly right on the circumference or the surface of the sphere, right? So we're in pretty good shape here, right? So pretty nice way of verifying your work. So the next problem gives a line segment that represents the diameter. So this is a two-stepper, because you would then have to find the midpoint in order to find the center, and then find the distance from the center to the, I keep hitting that thing. I don't know why this happened. To the circumference or the surface. So I'm gonna go about this a different way. I'm gonna pop it into Geogebra first. All right, so I got the points. I'll expand the view a little bit so that we could actually see those points. Whoa, crash. That's something. Holy schmagooglies. Oh, it's as if the whole class didn't happen. Okay. Got a little worried, thought I lost everything. All right, so I got points A and B. So that's fine. That's great. Now, Geogebra, like Desmos, has a lot of built-in functions. And in a lot of cases, it is a matter of just typing and seeing what you come up with. Because, you could tap on function f of x, and you can look at what they have, go to ABC, go to this jammy over here, look at all the different options. Or you can just start typing the thing that it is, that you're trying to create. Like, for example, distance. Once you start typing it, it brings up a list of possibilities. It's a drop-down menu, but I don't think of it like a drop-down menu, because it very often fails. And so my preference, instead of looking at it as a drop-down, would be to just look at it as a list of suggestions, right? So I would say, okay, I got distance. I'm going to open parentheses, and then I'm going to indicate, okay, I can do a point and an object. I can do a point and a point, even though it's not listed here. A line and a line, a plane and a plane. So I'm going to type in A followed by B. So A, comma, B. And it'll give me the distance between the 2 points, right? So then you kind of start getting greedy. Now, when it comes back with the 9.17, you got to be kind of suspicious of that, because the distance formula involves a radical. So is this a rounded number? Probably. Or is it an exact value that just so happens to be 9.17? Not very likely. But this could be a strategy that you use where you say, hey, you know what? I got an idea. This may be actually a clean number. Let me give it a shot, right? What you can do, if you suspect that it is a rounded value, just square it. Kind of like if you're trying to fake knowledge of unit circle trig. Figure the answer is the square root of something. So square it and see what it is, right? So I now know the distance between the 2 points is the square root of 84, right? I want the radius, right? So radius is going to be half of that value. So distance between, it's labeled here as P and Q. So R is going to be equal to 1/2 radical 84. And you can go through the process of simplifying and such, but I would caution against that because it's an unnecessary step. If you think about what we did in the last example, we had a radical 173, and then what happened when we put it in the formula? We squared away the radical. So it ended up being irrelevant, right? So leave it in the radical form, even unsimplified, because you're just spinning your wheels, right? Another possibility, hey, maybe it'll find midpoint for us. Start typing midpoint, and you see one of the options is point to point, right? So midpoint. Open your parentheses. And then call on A and B. And it spits out the midpoint. So -1, 3, 1. So I should be a little bit more specific here. That's the midpoint of PQ. All right, which makes that the center. So now I have everything I need. That's great. Geogebra served its purpose. So my final answer is going to be x plus 1 squared, poor quality close paren there, plus y minus 3 squared plus z minus 1 squared is equal to, then I just have to square that radical 84 and square the 1/2. Well, radical 84 squared is 84. 1/2 squared is a quarter. The quarter of 84 is 21. So I have it at this point. And that's our equation of the sphere. All right. So the bottom stuff is really just notes that, and I encourage you to look this over, because all it's really doing is taking stuff that we talked about in 2 dimensions and applying it in 3 dimensions. All right. So when we get into vector magnitude, you see it's just the distance formula again, right? The unit vector in the direction of v is, you're taking the vector and dividing it by the magnitude of that vector. So an ijk, as opposed to just ij in 2 dimensions, now it has that third component corresponding with the z-axis. So like I said, this is a short one because there's really nothing new here. This is all stuff that we've seen before, and all it is just applying it in 3 dimensions, right? So definitely have a look at this because it's really important, right? So that's where we're ending the unit. Let me pause the video. I can actually stop recording.